Ok, adesso stiamo registrando. Dunque, passiamo alla slide, dovreste vedere la slide in questo momento. Allora, la volta scorsa abbiamo iniziato questo nuovo modulo che riguarda sostanzialmente le simmetrie discrete, che oggi svilupperemo e porteremo a compimento, e poi la prossima volta faremo dei problemi, degli esercizi su questa parte qui. Vi ricordo che la volta scorsa, l'ultima parte della lezione, abbiamo discusso di fermioni e bosoni, e quindi sostanzialmente della simmetria della funzione d'onda per sistemi di bosoni identici e sistemi di fermioni identici. Okay, abbiamo ricavato quali sono le relazioni tra il momento angolare orbitale e lo spin L ed S, affinché la funzione d'onda totale di un sistema di due fermioni sia antisimmetrica per scambio di fermioni identici, e invece quella per bosoni sia simmetrica per scambio di bosoni identici. Oggi ovviamente faremo uso anche, diciamo, di queste cose che abbiamo visto la volta scorsa, ma andiamo adesso più in profondità per quanto riguarda appunto le simmetrie discrete. Allora, so let's start with slide 1. So let me recall you what we have said already before about transformations. So there are different types of transformations that act, for instance, on a wave function of a physical system. And first of all, we can split transformation into two main groups: the discrete transformations that we will discuss today, and the continuous transformations that we have already started discussing in the past lessons, such as rotations, for instance, etc. We have seen the case of finite and also infinitesimal rotations, if you remember. And then furthermore, continuous transformation can be further split into space-time transformations and internal transformations, where internal transformation means that this transformation acts on the internal quantum numbers of the physical system. Now, a few more words. As you already know, examples of continuous transformation are translations or rotations. And in general, any finite transformation can be obtained through an infinite sequence of infinitesimal transformations. And this we already applied in our example for rotation, if you remember. And another important feature of continuous transformations is that conservation laws are additive, in the sense that the sum of the quantum numbers is the conserved quantity. Now, what about discrete transformations? The parameters of the discrete transformation can only take discrete values. That's the reason why we call them discrete transformations. So in this case, you cannot obtain, the finite transformation from an infinite sequence of infinitesimal transformation. Of course, this makes no sense at all for discrete transformations. And in this case, the conservation laws are multiplicative, in the sense that it is the product now of the quantum numbers that is conserved. Another difference between continuous and discrete transformation is the following. So while continuous transformations are associated to the exponential of the corresponding operator, for instance, here we have the charge operator, capital Q, discrete transformations are defined directly by the corresponding operator. So U can be either the parity, charge conjugation, time reversal, as we'll be studying today. However, in general, if a transformation described by an operator U corresponds to a symmetry of a physical system, then one expects that the U operator commutes with the Hamiltonian of the physical system, and of course that the physics must be unaffected by this transformation. So for instance, this we have seen already, if you consider the probability for a transition between a transformed state psi into a transformed state phi, okay, this must be equal to the transition probability for the untransformed state psi and phi. And this is only possible if the U operator is a unitary operator, such that U daga U is equal to the identity matrix. Okay. Now, so the parity operator, let's start with parity. So the operator of inversion of spatial coordinates that we have seen already last time, so R into minus R, is an example of a discrete transformation. And this transformation is produced by the parity operator that we label with the capital P. Okay, so let's move to the blackboard. So suppose we apply now the parity operator over a certain wave function of r, then as a result, we're going to have the wave function of minus r, okay? So the parity operator acts in such a way to invert the spatial coordinates. Clearly, what happens if we apply twice the parity operator on a wave function? Of course, we expect that we return to the original wave function. So if we take this to the square, this corresponds to have the parity operator acting on the parity operator, in turn acting on the wave function. That is, the parity operator acting now on the transformed wave function, where now the coordinates have been inverted. And when we inverted again the coordinates, we obtain, of course, the original wave function. So if you now take the first term and the last term, okay, this is nothing else than the eigenvalue equation for p squared. And clearly the eigenvalues of p squared, the eigenvalue can only be +1, right? So if we now take now the p operator, so the parity operator, then one expects that the only possible eigenvalue of the p operator can be plus or minus 1. Okay, we take the square root. So what is now the meaning of a parity +1 or a parity -1? So a wave function may or may not be, in general, an eigenstate of parity. Suppose that the wave function it is an eigenstate of parity. So we have two cases. The case where the parity is even, this corresponds to the eigenvalue p equal +1, okay? And as an example, we can consider the cosine. Suppose that your wave function is just the cosine of x, okay? So when you apply the parity operator over your wave function, you're gonna have cosine of -x. But the cosine is an even function, so this is equal to the cosine of x, and so this is equal to the original function. And as a consequence, if you want to write the eigenvalue equation, you get p of psi equal to +1 psi. Okay, so the eigenvalue in this case is +1. We can have, of course, an example for p odd. So the parity is odd whenever the eigenvalue of p is -1. And the obvious other example is the sine function. So psi is equal to sine of x. Then you apply your parity operator, that is the sine of -x. But now the sine is an odd function, so this corresponds to minus sine of x, and so to minus your original wave function. And so in this case, when you apply the parity operator over psi, you're going to have -1 psi, okay? So for p odd functions, the eigenvalue of parity is -1. Okay, so a function can be eigenstate of parity operator with eigenvalue +1 or -1, but it can also be not an eigenstate of parity operator, okay? So suppose an example like this, so psi is equal to cosine x plus sine x. So this function here have not a defined parity. In fact, if you apply now the parity operator on this, you're going to have cosine of -x plus sine of -x, that is cosine of x minus sine of x. And it is, of course, different from the original wave function. Okay, so this is an example of function that has not a defined parity. So psi in this case is not an eigenstate of p. And of course, no eigenvalue exists in this case. Now, back to the slide. So what does the parity operation? It does invert the spatial coordinates, as we know, so from r to -r.
It also inverts the momenta, okay, because it inverts the direction of motion. So we move from positive momentum to negative momentum. It does not invert the time, so time remains the same. And also it does not invert, for instance, angular momenta. Angular momenta classically is defined as the vector product of r times p, but then since both get transformed, get inverted, okay, you have two minus sign. So at the end, you end up with unchanged angular momentum. And this, of course, also applies to the spin, because the spin is also an angular momentum, okay? So orbital angular momentum and spin are not affected by the parity operation. This we can generalize this. So in general, a vector, such as position vector, momentum vector, electric field vector, whatever vector, will be inverted under parity transformation, while the cross product or the vector product of two vectors, such as the angular momentum, magnetic field, etc., will not change under the parity operation. And the latter is called a pseudo vector or axial vector. More, the scalar product of two vectors is a scalar by definition, and it is invariant under parity transformation. And as we will see, this is the reason why parity is conserved in quantum electrodynamics and in quantum chromodynamics, so by electromagnetic and strong interactions. On the other hand, the scalar product of a vector and a pseudo vector is a pseudo scalar, and it does change sign under the parity operation. And as we will study, this is the reason why parity is not conserved in weak interactions. Now, a particle can be in an eigenstate of P only if it is at rest. So in general, if you have a system of n particle, okay, this system can be in a parity eigenstate only in the center of mass system, where the total momentum, of course, is zero by definition. Let's now derive the form of the parity operator when acting on a Dirac spinor. So we move back to the blackboard. Ok, mi fermo un attimo solo per chiedervi se avete sentito bene, visto tutto, se è tutto a posto.
Per me sì.
Ok,
Sì.
Va bene, grazie. Ok, quindi vediamo adesso qual è la forma di questo operatore, la forma matriciale di questo operatore di parità quando lo applichiamo noi a uno spinore, quindi a una soluzione dell'equazione di Dirac. Ok, so suppose now that psi of t, x, y, z, okay, is a solution of the Dirac equation. So it is the usual four-component spinor, okay? So we can write down the Dirac equation in a more explicit way, like I, gamma 0, the psi in the t. So we explicit all the derivatives, plus I, gamma 1, the psi in the x, plus I, gamma 2, the psi in the y, plus I, gamma 3, the psi in the z, minus the mass term equal to 0. So this is just the Dirac equation. Okay. Let me call this equation 1. Now, what happened when we apply the parity operator on our spinor? What is the effect of this operation? So we apply P to psi t, x, y, z, and we're gonna obtain psi prime of t prime, x prime, y prime, z prime. That is the parity transformed wave function or spinor that we can also write equivalently as psi prime of t, which remains the same, and then minus x, minus y, minus z, because the parity operator just inverts the spatial coordinates. This is 2. So what we have here, this psi prime is the transformed spinor after the application of the parity operator. And of course, if we apply now the parity operator over the transformed operator, we're going to obtain the original spinor. So of the original, of the transformed spinor. So P over psi prime is equivalent to P that acts on p psi, that is p squared psi. And as we have seen, if you apply twice the parity operator, you obtain the original state. So this is equivalent to applying the identity operator over psi. And so this is just psi, of course. So we can also express psi as the parity operator acting on the transformed spinor. And this is our third piece. So now we can substitute this expression, so equation 3 into equation 1, so direct equation. And so we will obtain now I gamma 0 p on the psi prime in the t plus I gamma 1 p the psi prime in the x plus I gamma 2 p the psi prime in the y plus I gamma 3 p the psi prime in the z minus m p psi prime equal to 0. Okay, so we just substituted 3 into 1. Now let's multiply on the left by gamma 0. And also we remember that, of course, x is equal to minus x prime, y is equal to minus y prime, z is equal to minus z prime, and t is equal to t prime. So when we do so, we obtain I gamma 0 p the psi prime in the t prime minus I gamma 0 gamma 1 p the psi prime in the x prime minus I gamma 0 gamma 2 p the psi prime in the y prime minus I gamma 0 gamma 3 p the psi prime in the z prime minus m gamma 0 p psi prime equal to 0. Okay. Let's now make a last manipulation on this equation. So we now use the anti-commutation rule that you know gamma 0 gamma k is equal to minus gamma k gamma 0, okay, where k runs from 1, 2, and 3. So this allows to essentially to swap the order of gamma 0 with gamma 1, gamma 2, and gamma 3, and to change sign. So once we do so, we're going to obtain I gamma 0 p the psi prime in the t prime plus I gamma 1 gamma 0 p the psi prime in the x prime plus I gamma 2 gamma 0 p the psi prime in the y prime plus I gamma 3 gamma 0 p the psi prime in the z prime minus m gamma 0 p psi prime equal to 0. And this we call equation 4. Okay, so in the last passage we just swap the order of the gamma 0 with the gamma k, with k 1, 2, 3, and so we had to change sign for each of these terms. Now we have to realize that the transformed spinor psi prime is also, of course, solution, must also be solution of the Dirac equation. So I gamma mu de mu minus m psi prime equal to 0, okay? So if psi is a solution, also psi prime must be a solution of the Dirac equation. So we can write this in more explicitly as I gamma 0, like equation 1, the psi prime in the T prime plus I gamma 1, the psi prime in the X prime plus I gamma 2, the psi prime in the Y prime plus I gamma 3, the psi prime in the Z prime minus M psi prime equal to 0. And this is our equation 5. Okay. And now we are done because we can just compare equation 4 and equation 5. And you see that the two coincide only if gamma 0 is just the identity matrix. Just realized by comparing equation gamma 0, we multiply by another parity operator, IP. Now, when you apply twice the parity operator, this is again the identity matrix, I. And so at the end, we obtain that the parity operator coincides with the gamma 0 matrix. So this is our result. And so, sorry, when we apply this on a wave function, obtain that psi into the transformed psi prime, which is the parity transformed psi, or equivalently, the psi multiplied by gamma 0. Okay, so all these boring algebra was just to show that the parity operator acting on a spinor is just has just the same effect of acting the gamma 0 matrix on our spinor. Now, we have to introduce now the concept of intrinsic parity. So each elementary particle, either a boson or a fermion, has an intrinsic parity. And the intrinsic parity of a fermion field, for instance, is defined by the action of the parity operator, so of the gamma 0 matrix, on the spinor corresponding to that fermion at rest. Okay, so we can define, of course, the parity for a particle only if it is at rest, as we mentioned before. And so the intrinsic is defined by the action of gamma 0 max on the corresponding spinor at rest. So let me change page here. So let's consider, for instance, the U1 solution of equation. Okay, if you remember, this is the normalization. Sorry, the normalization constant. Then we have 1, 0 L over plus M px plus I py divided E plus M. And when we put this at rest, all the momenta goes to 0, the energy goes to 0 essentially, so we're going to have just the mass here and then 1, 0, 0, 0. And we can do the same for the V1, for instance. This U1, if you remember, is for the first solution for a particle. V1 is the first solution for the antiparticle. So the full expression of V1 is Px minus I Py over E plus M minus Pz over E plus M 0, 1. And so when we go at rest, this reduces simply to square root of M and then 0, 0, 0, 1. So let's now apply the parity operator. Let's start with U1. So this is equivalent to apply the gamma 0 matrix of U1. And the gamma 0 matrix, if you remember, is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, acting on our spinor, that is 1, 0, 0, 0. Okay, so when you multiply this matrix with this vector, you realize that you obtain exactly the vector itself. 1, 0, 0, 0, that is plus 1 u1. Now we do the same exercise for instance, the V1 solution, the anti-fermion solution. So that is gamma 0 V1. So the matrix is of course the same, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, acting now on square root of m, and then we have 0, 0, 0, 1. And once you do so, you obtain square root of m of 0, 0, 0, minus 1, that is minus 1 square root of m, 0, 0, 0, 1, and so minus 1 V1. And then similarly, you can do by exercise, you would obtain that P acting on the second particle solution will be also plus 1 U2, and P acting on the V2 solution will be also minus 1 V2, okay? So we have obtained now 4 eigenvalue equations for the parity operator acting on U1, U2, V1, V2 Dirac solutions, okay? In two cases, U1 and U2, you get a plus 1 eigenvalue, so even parity. In the other two cases, you get a minus 1 eigenvalue, so for the anti-fermion, so odd parity. Okay. So let's see this again on the slide. So let me repeat what we've just done. So each elementary particle has an intrinsic parity, and the intrinsic parity of a Dirac fermion is obtained by the action of the parity operator on the spinor, okay, at rest. So we just obtain this evaluation, and so what we can do is that intrinsic parity of a fundamental spin particle opposite to that of the spin 1 alpha antiparticle, okay? It is plus 1 for U1 and U2, it is minus 1 for V1 and V2. The intrinsic parity of quarks and charged atoms and their antiparticle, therefore, like, okay, is by, okay. So for fermions, we're going to have plus 1 for the electron, the muon, and the tau, and plus 1 for all the 6 quarks, up, down, strange, charm, bottom, and the top. And correspondingly for the fermion, we're going to have the minus sign, the minus 1 intrinsic parity. Okay, so these are all the antiparticles. What about the neutrinos? So we didn't put neutrinos here, and that neutrinos can only interact through weak interaction because they don't carry electric charge, they don't carry core charge. But as we just mentioned, interaction violate parity, conserve parity. We cannot assign a parity eigenvalue to neutrinos. Okay. Now, let me introduce another very important quantum number, that is the baryonic number. And the baryonic number of a given physical state is given by the number of baryons minus the number of antibaryons in general, okay? And the thing that you have to remember is that the baryonic number is conserved in every kind of interactions. So a strong, electromagnetic, weak, any kind of process, decay, reaction, whatever, the baryonic number is always conserved. So in order to ensure conservation of the baryonic number, baryons can only be produced in pairs, okay? So you cannot produce in a reaction just one baryon or one antibaryon, but you have to produce a system of baryon and antibaryon, okay? So for instance, you have a proton-proton that goes into proton-proton, and then you create a pair of proton-antiproton, okay? Therefore, the parity conservation in strong and electromagnetic interaction requires that baryons and antibaryons must have opposite intrinsic parity. So in order to have the same parity in the initial state and the final state, okay, obviously the parity of this baryon pair must be 0. That corresponds to say that the intrinsic parity of the proton must be opposite to that of the antiproton. And this is general for baryons and antibaryons, okay? Now, the choice of the actual sign of the intrinsic parities of baryons and antibaryons is only a matter of convention, okay? And for instance, by convention, the intrinsic parity of protons and neutrons is chosen to be positive, +1, and the intrinsic parity of the corresponding antiparticle, so antiproton and antineutron, is assigned to be negative, -1. Okay? So let's now derive the eigenvalue of the parity operator for a system of n particles. And so we have now to apply what we have learned at the end of the last lesson. So let me move on forward. So as we have seen last time, okay, so the spatial inversion from R to -R corresponds in polar coordinates, moving from theta to theta prime given by pi minus theta, from phi to a prime given by pi plus phi, whereas the radial component stays the same, isn't changed. Okay, and so if you remember from the last time, okay, so if we start from psi of -R, okay, this we can write up as psi of R prime, and then we have the spherical harmonics of theta prime, phi prime, okay? So the radial part stays the same because R is equal to R prime. But then if you remember, the spherical harmonics, it's an addition -1 to the L factor, okay? Compared to the untransformed one. And so overall, we're going to have -1 to the L times psi of R, okay? Now, since the parity operation indeed corresponds to the inversion of the spatial coordinates, it follows that the parity of the wave function is given by exactly -1 to the L. So this is +1 if L is even. And so in this case, you get even parity. Or to -1 if L is odd. And so in this case, you're going to have a odd parity. Now, let me remember you that being related to a discrete transformation, parity is negative quantum number. So if you have a composite system of particles, parity of this system will be proportional to the product of the parities of the individual wave functions. Okay. However, compute the parity of one has also to consider the intrinsic parity of each particle, the eigenvalue of P, the particle at rest. Suppose now we have a wave function for a system of n particles. So we have R1, R2, Rn. Okay, we apply the parity operator on top of this, and so the result will be the transformed wave function with the inverted coordinates -R1 -Rn times the intrinsic parity of each of the system. So P1, P2, Pn. And now the transformed wave function is just the original one times -1 to the L. So we're going to have pi1 times pi n, then -1 to the L, and then the original wave function, the untransformed. So R1, R. So now consider again first member and the last member, okay? So this is the eigenvalue equation for the parity operator for a case of a system of n particles, and the eigenvalue of P is minus 1 to the L times the product of all the intrinsic parities. Okay, so the value of this product of this give you the eigenvalue of P for this system of particles. And let's now consider a simple case of a two-particle system. So in this case, clearly, the eigenvalue of parity will be minus 1 to L12 times P1 times P2, where L12 is the orbital angular momentum of the two particles in their mutual center of mass frame, so the relative orbital angular momentum, okay, of the two particles, and P1 and P2 are the intrinsic parities of the two particles in the system. For the case of three particles, okay, it is similar but a little bit more complicated. Because in this time, you have to calculate the overall relative orbital angular momentum. So suppose you have particle 1 here, particle 2 here, and this is L12. But then you also have a third particle here. And so you're going to have also an L3, okay, where the L3 is the orbital angular momentum of the first particle relative to the center of mass of particles 1 and 2. Relative to the system of particles 1 and 2. So let's consider, for instance, the case now of baryons. So we know that baryons are a system of three quarks, so Q, Q, Q systems. Okay, so the parity of a baryon is going to be minus 1 over the total angular momentum, so L Q1, Q2 plus L3, LQ3. And then we have the intrinsic parities of the three quarks, sorry, PQ times PQ times PQ. Let me add me something in the previous page, but this I don't know. Yes. So back on the previous page, let me just I forgot to generalize this. So in the previous page on the bottom, you just add this. Okay. So the parity will be minus 1 to the L dot. Okay, what we are now applying here times P1, P2, P3. That is minus 1 to L12 plus L3 times P1, P2, P3. I forgot to give you this, but this is what we are now applying to the case of baryons, okay? What about antibaryons? Antibaryons are a system of three antiquarks, Q bar, Q bar, Q bar, okay? And so the parity of antibaryons is equal to minus 1 to the L Q bar 1, Q bar 2 plus L Q bar 3. And then we have the parity, the intrinsic parity of the antiquarks. Now, if you remember, the intrinsic parity of fermions, so of quarks, is plus 1, and the intrinsic parity of antifermions, such as the antiquarks, is minus 1. So if you go back now to the baryon case, this is minus 1 to LQ1, Q2 plus LQ3 times 3 times plus 1, so plus 1 to the 3, to the third power, which adds an additional, which is of course +1. And so we get -1 LQ1 LQ2 plus LQ3. Okay, so this is the eigenvalue overall for of the parity for a baryon. If you now go back to the antibaryon, we remember that the intrinsic parity of antiquarks is -1. So this is going to be -1 L Q bar 1 Q bar 2 plus L Q bar 3. Then we have a -1 to the third, and this adds an additional minus sign here. So this is going to be -1 to L Q bar 1 Q bar 2 plus L Q bar 3 plus 1 to account for the additional minus sign. And so overall, this is minus the parity of a baryon. Okay, the difference is just an additional minus sign coming from the fact that the intrinsic parity of antiquarks are negative and the intrinsic parity of quarks are positive. Okay, so let's now come back to the slide. So this was for fermions. Okay, what about now bosons? Now, differently from fermions, bosons and antibosons have the same intrinsic parity. So intrinsic parity is opposite for fermions and antifermions, but it is the same for bosons and antibosons. Furthermore, of course, bosons do not require the baryonic number to be conserved because bosons are bosons, they are not baryons. And so there is no request for bosons to be created in pairs. And so they can be created alone. And as a consequence, their absolute parity can be defined without ambiguity. And in some cases, it can also be measured experimentally. Okay. Now, for bosons in general, the following applies. Okay, so the intrinsic parity of the gauge bosons of the three elementary interactions is negative. So the parity of photon, the parity of gluons, the parity of the W and the Z is all intrinsic parity is always -1. What about now the parity of mesons? Mesons, if you remember, are now Q-bar systems, such as the pion, for instance. And so you apply the general rule. So the parity of a meson is -1 to the relative momentum of the two quark-antiquarks, okay, times the intrinsic parity of the quark times the intrinsic parity of the antiquark. So this stays the same, but now we have the product of a +1 times a -1, which gives you an additional -1. So the parity of the mesons is -1 LQQ bar plus 1, coming from this minus sign here. Now, what about now the lightest mesons? Okay, the lightest mesons are also called the low-lying mesons, as we'll be studying next. Okay, and these mesons come with the 0 orbital angular momentum. Okay, so once you put a 0 here in the L, okay, you understand that the parity of a low-lying meson must be -1 to the first, so -1. And in fact, it turns out, and this has been also measured, that the intrinsic parity of pions, which are in fact the lightest low-lying mesons, is indeed -1. Okay, so this quantity was measured by requiring the conservation of angular momentum in the strong absorption process, where a pi minus is absorbed by a deuteron and resulting in a neutron pair, and imposing that the wave function of the two final state neutrons is antisymmetric because they are indistinguishable. Okay. If you are curious, you find the details of these in the textbooks, okay? But the main point here is that pions are low-lying mesons, so they come with 0 orbital angular momentum, and as a consequence, their intrinsic parity must be -1. Let's also generalize this, okay? So pions not only have L equals 0, but also have S equals 0, okay? This we will see next also in the course. And so the total angular momentum of pions, which is L plus S, is 0 because both L and S are 0. Okay, and so they are classified as pseudo-scalar mesons. So if you look at the quantum number Jp, where J is the total angular momentum and P is the parity, okay? J is 0 because it is the sum of two zeros, and the parity must be -1, okay? So we call this 0 minus. And objects that have 0 minus JP quantum number are called pseudoscalar mesons. Bosons with quantum numbers 0 plus, 1 minus, or 1 plus instead are called respectively scalars, vectors, and axial vectors. Okay. Now this table more or less summarizes the properties of parity for some particles. So for the photon and also for all the other gauge bosons, the intrinsic parity is -1, and these are all vectors. Okay, so the JP quantum number is 1 minus. For pions, as we just seen, the parity is -1, and they are pseudoscalar, so they all come with 0 minus quantum numbers. The kaons, which are, let's say, the heavier brother of the pions, where now we have also strange quarks, as we will study, they are also pseudoscalar, just like the pions. So both have negative parity and 0 minus JP quantum numbers. Then we have here example of vector mesons, the rho, the omega, the phi. So these are vector objects, so they come with the angular momentum 1, but the parity is still negative, 1 minus. Then what about fermions? So the proton, by convention, the parity, intrinsic parity is +1 and the antiproton -1. And then they are fermions, so the total angular momentum is just given by the spin because they also come with L equals 0. So is 1/2, and then plus and minus parity. And same for the neutrons and the antineutron. Okay. So for a system of two bosons with the same intrinsic parity, one has that the overall parity eigenvalue is -1 to the L, and then the square of the intrinsic parity. We are supposing that they have the same parity, so they just come intrinsic parity, so this comes to the square. So whatever it is, either +1 or -1, when you square it, it gives you just 1. So for a system of two bosons with the same intrinsic parity, the parity is given by -1 to the L, simply. If the bosons have also spin equals 0, like for instance pion pairs, then J is equal to L, and the only possible parity angular momentum assignments are the following. So when L is 0, J is 0, okay, and the parity is plus, okay. You get 0 here, you get -1 to the 0, which is +1. When L is equal 1, then also J is equal 1, and the parity is negative, so 1 minus. When L is 2, okay, J is also 2, and then you put the 2 here, you get the +1, and so on, okay? So 0 plus, 1 minus, 2 plus, 3 minus, and etc. If the two bosons are identical, of course, one also to require that the total wave function must be symmetric under exchange of identical bosons. And as we have seen the last lessons, we have to require that L plus L are even. So L plus S, so J must be even, okay, as we've seen at the end of the last lessons. In particular, for pairs of spin 0 identical bosons, so for instance, pi0, pi0, L must be even because S is 0, and so J must be 0 again. J must be even. And the only possible assignment, therefore, are 0 plus, 2 plus, 4 plus, etc. Okay, this is the only way to account for the fact that the wave function for identical bosons must also be symmetric. Now, as we already mentioned before, parity conservation is not a universal law of physics. It is experimentally demonstrated that electromagnetic and strong interaction conserve parity, but the weak interaction do not. So weak interaction violate parity, and this we will study ahead in the course. In particular, this was discovered experimentally by Madame Wu in 1957 with a very smart experiment that revealed for the first time that parity, in fact, is not conserved in weak interactions. This we will study next in the course. What about now parity conservation in QAD? Okay, so this at least we have to show now. So parity conservation in QAD arises naturally from the form of the interaction. And so let me show you this just for the simple case of the molar scattering that we know now very well. That is the scattering of an electron through the exchange of a virtual photon at first order. So let me move back to the blackboard. All right. So this is now page 6. So let me draw again the Feynman diagram for the molar scattering. So we have an incoming electron, an outgoing electron, and a photon, another incoming electron, and an outgoing electron. And the four momenta are P1, P2, P3, P4. Then if you remember, we label these like the mu vertex, the upper vertex, and the lower vertex as nu. So this is the molar scattering, and we have already derived the matrix element for this process. Okay, so starting from first principles and then applying the Feynman rules. So if you remember, the results is that minus E squared, then you have the adjoint spinor of P3 gamma mu U P1. Then we have the photon propagator. And then we have the current at the lower vertex. So U bar P4 gamma nu U P2. And this we can also write, if you remember, in a compact way as minus E squared over Q squared, and then we have the scalar product, okay, of the two currents at the upper and lower vertex. Okay, we put here in parentheses mu and nu to indicate just one is on the upper vertex and the other is for the lower vertex. So overall, the important thing is that the matrix element at the end is given by the scalar product of two vector currents. Okay, so let's see now how this behaves under the parity transformation. Okay. So the equivalent matrix element for the parity transformed process, where now the three momenta of all particles are reversed, can be obtained by applying the parity operator to the spinors. Okay, so let me remind you that when you apply the parity operator of the spinor U, you obtain the spinor U prime, and this corresponds to applying the gamma zero matrix over the U spinor, and similar for the adjoint spinor. So this is going to be U P, and so U gamma zero. Okay. More properly, when you have an adjoint spinor, the operator should act from the right to the left, as it is written here. So let's now write down the parity transformed vector current at the upper vertex. So the J E mu prime, where prime means parity transformed. So this is U bar prime P3 gamma mu and U prime P1. That is U bar P3, where now the gamma zero metric, so the parity operator is acting from the right to the left. Then we have our gamma mu, and then we have the gamma zero acting on the P1 untransformed spinor. So this is general now for the vector, where of course the Lorentz index runs from 0 to 3, 1, 2, and 3. So let's consider separately the zero component. So the JE0 prime, this is going to be U bar gamma 0, then we have another gamma 0, and then another gamma 0 U. Okay, this comes from the previous line, but now applied to the zero component only. And then you remember that gamma 0 squared is just the identity matrix. So this is equal to U bar gamma 0 U, which is indeed the untransformed zero component of the current at the upper vertex. What about now the spatial components? So the JEK, where K runs now 1, 2, and 3. So this is going to be U bar gamma 0. Then we have gamma K, then again gamma 0 U. That is, now we apply again the anti-commutation rule of the matrix, the gamma matrices. So this is minus U bar. We swap the order of gamma K and gamma 0. And again, we obtain a product of two gamma zeros, which give you an identity matrix. So this is minus U bar gamma K U. That is now minus the untransformed current for the spatial components. Okay. So having now this in mind, we can calculate the scalar product that enter into the matrix element. Okay. So J E mu prime scalar J E nu prime. Okay, so it's a scalar product of two vectors. So this is the product of the zero components transformed minus the product of the spatial components transformed. So now we have the zero components are unchanged by the parity transformation. So they coincide with the untransformed, whereas the spatial component gets an opposite sign. So we have a minus GAK for the first one and a minus GAK for the second. But now we have the product of two minus sign, which turns back a plus sign. So this corresponds to GE0, GE0 minus GEK, JEK. That is exactly the untransformed scalar product. So although the spatial component gets an opposite sign when applying the parity operator, when you compute the overall scalar product, the opposite sign cancels because you have it twice. And so overall, the scalar product of the two vector currents results unchanged or unaffected by the parity operator. Okay. And since this is the core of course, of our transition matrix, it turns out that the parity transformed transition matrix, if you like, MFI prime, corresponds to the untransformed one. And so parity is conserved. And this is in general in all QAD processes. So back to the slide. One last thing before we stop for a while. So we can conclude that the QAD matrix element is invariant under parity operation. And more in general, in terms of the terms of the Hamiltonian or the Lagrangian, if you like, which are related to the quantum electrodynamic interaction, are all invariant under parity transformation. And therefore, parity is conserved in electromagnetic interactions. What about the other interactions? Now, as we will study, also the QCD vertex has the same structure, the same vector structure, U bar gamma mu U. Okay, we also have here additional color terms, okay, factors, but the structure of the current is still a vector current. And so, using the same argument that we just applied for a QAD process, we also would obtain that parity is conserved in all strong interactions, just because the interaction has the same form, is a vector current. Okay. On the other hand, as we shall see, the weak interactions have a different structure of the vertex interaction. For weak interaction, we don't have anymore a simple vector current, but a more complicated object that we study. And as we will show, as a consequence, parity is not conserved. Okay, we're going to have an additional minus sign in the matrix element when we apply the parity operator. Ok, ok, direi ci possiamo fermare qui per una pausa, possiamo ricominciare alle 10:15. Se avete domande, ovviamente, potete farle adesso. Dunque, Andrea Di Donna, riesci a sentirmi? Sei connesso? Allora possiamo riprendere, ci siamo tutti?
Ok, sentiamo.
Proprio che l'abbiamo sentito un po' male.
Ah, ok, niente, volevo solo dire a lui, mi ha ancora dato la mail. Va bene. Allora possiamo riprendere, adesso faccio di nuovo lo sharing. Allora questo lo possiamo chiudere. Questo lo apriamo, questo lo apriamo. non so, riuscite a vedere il schermo? Ah, ecco, sta prendendo. Ok, adesso dovreste vedere tutto il mio desktop. Allora, va bene. Allora, abbiamo diciamo, sviscerato più o meno in tutte le sue forme la prima delle trasformazioni discrete che studieremo oggi, che è appunto l'operatore di parità, che ha come effetto quello di scambiare le coordinate iniziali da R a meno R sullo spinore o in generale sulla funzione d'onda alla quale si sta applicando. Adesso andiamo a studiare un'altra trasformazione discreta che è quella della charge conjugation. So the charge conjugation operator that we will label as capital C, acting on a particle state, reverses the sign of the charge, while leaving the momenta, position, spin and time unchanged. Quindi passiamo un attimino qui alla lavagna e molto brevemente vediamo cosa fa questo operatore. So let's consider a particle of charge q described by the wave function of psi q. So when we apply the C operator of this wave function, which depends on the charge q, then the result is the wave function of the opposite charge. So it reverses the sign of the electric charge. And again, if you apply now the charge operator twice, we're going to obtain the original state. So this is equivalent to use this over psi q, that is C bar over the transformed wave function. So we get back, of course, the original wave function. And so the eigenvalue equation for the squared charge operation operator is 1 psi q. Okay? And so the eigenvalue of the C operator must be, again, either plus or minus 1. And these are called the C parities. Okay, either even or odd in analogy to the parity operator. Now, let's come back to the slide. Actually, the charge conjugation operator does not only invert the electric charge, but it changes the sign more generally on all additive quantum numbers. So electric charge, baryonic number, lepton-flavored number, etc. Similar to parity, charge conjugation is conserved by electromagnetic and strong interaction, but it is violated by the weak interactions. Now, let's see what happens when we apply the charge conjugation operator to a charged particle. Okay, so clearly, if you apply the charge conjugation operator to the proton wave function, you invert the charge of the proton. So at the end, you're going to have the antiproton state. Similar, if you work on the electron, you're going to have the positron. If you go to the pi minus, you're going to have the pi plus, etc. And so since the initial state and the final state are different here, let's say the transformed, the untransformed state are different, clearly charged particle cannot be eigenstates of the charge conjugation. This is only possible for neutral particles that coincide with their own antiparticle. Okay, so suppose there is X is just a generic neutral particle. If it is identical to its own antiparticle, okay, so X0 is equal to X bar 0, then X0 is an eigenstate of the charge conjugation operator with eigenvalue either +1 or -1. Now, this does not apply to neutrons. You know, neutrons are, of course, neutral particles, because it turns out that the neutron and antineutron have opposite magnetic dipole moments, which is respectively parallel and anti-parallel to the spin, and are thus distinguishable. So this request here is not fulfilled for neutrons and antineutrons. What about photons? So one can make the following reasoning. So photons, are emitted by accelerated charged particles, and this is the Bremsstrahlung emission, as you know, okay? But these accelerated charged particle would change sign upon the application of the charge conjugation operator. And so this suggests that the intrinsic parity of the photon must be -1. So the photon is eigenstate of C with eigenvalue -1. And since C is a multiplicative operator, for a system of n photons, one must have this kind of eigenvalue equation. So you have a system of n photons, then the eigenvalue of this system must be -1 to the n. Okay, so it's positive depending if n is even, is negative if n is odd. Now let's consider the pi zero. Okay, the pi zero, first of all, is a neutral meson, and it does coincide with its own antiparticle. So pi zero and anti-pi zero are exactly the same object. And so clearly it must be an eigenstate of C. Now, as we will study, the pi zero decays electromagnetically into two photons, so the pi zero into gamma gamma, and this happens almost all the time, so with the probability or a branching ratio of 99%, okay? Therefore, the conservation of C in electromagnetic interaction requires that when you apply C to the pi zero is equivalent to apply C to the final state, which is gamma gamma, okay? But then you have a system of two photons, so you're gonna have this additional factor of -1 to the 2, which gives you a +1, okay? So if you now compare the initial, the left-hand term and the right-hand term of this equation, it is nothing else than the eigenvalue equation for the pi zero with the eigenvalue +1. So the pi zero is eigenstate of C with eigenvalue of the charge conjugation equal to +1. What about the following decay? Pi zero into 3 gamma. Charge, of course, is conserved because it is 0 in the initial state. It is also 0 in the final state. Then energy and momentum can also be conserved if the momenta of these final state photons are proper, okay? However, it is experimentally proved that this decay is not observed. It is impossible, okay? You see that the branching ratio of the pi zero to 3 photons compared to the pi zero to 2 photon is completely neglected. We have an upper limit of 3.1 10 to the minus 8. Why? Because this electromagnetic decay would violate conservation of the charge conjugation. In fact, when you have now a system of 3 photons, here you're going to have -1 to the third, which gives you a minus sign. Okay, so this would lead to a state of negative C parity, and therefore it is forbidden by C parity conservation in electromagnetic process. And in fact, it is the only rule that forbids this decay to occur in nature. Okay, it's just because charge conjugation is conserved in electromagnetic processes. Now, what about if you have now a pair of charged particles, okay, with opposite sign? So overall, this is a neutral object, for instance, a pi plus pi minus. So eigenstate of C can, in fact, be constructed from particle-antiparticle pairs, charged first, overall neutral, in the radial mass system. So let's consider, for instance, the pi plus pi minus. When we apply the charge conjugation operator to our pi plus pi minus system, we invert charges of these two pions. So it's pi minus. We're gonna have pi minus and plus. Then we can get back to the original state if we just invert their position. So if you apply essentially the parity operator here, okay. So the net effect of the charge conjugation in this case is the exchange of the two mesons, and this coincides with the application of the parity, and this explains why we have this -1 to the L factor here. Okay, so this is in fact the eigenvalue equation for a pi plus pi minus system, and the eigenvalue is -1 to the L. So it depends on the value of the orbital angular momentum relative to the two pions. Now, if the two particles have a non-zero spin, such as fermions or vector meson, then the result is not that simple, because the charge conjugation affects not only the spatial component of the function, as was here, but also the spin component. Remember from the last lesson, the total wave function can be in general split in spin function. And the symmetry of the wave function is different for the components. So essentially one has, if you apply the charge conjugation in this case for particle with spin, you have to swap not only the position of the particle, but also the spins. So let's see now how this applies. So back to the blackboard. So let's distinguish two cases. The first case is pairs of bosons with spin different than 0. And the example could be, for instance, the ρ plus ρ minus vector meson. Okay, vector means that the spin is 1. It's not 0, but is 1. Okay. So what happened when we apply the charge operator conjugation operator to this system? So we have the ρ plus ρ minus. Okay. So as we've seen for the charged pions, we have to swap them. This gives up a -1 to the L factor. But then we have also to swap their spins. So this, if you remember from the last lesson, gives you an additional -1 to the less factor. Okay, so this last term here arises from the symmetry of the spin component of wave function. So overall, this is given by -1 to L plus S, and then we have our ρ plus ρ minus state. Let's consider, as another example, a pairs of fermion. For instance, E plus, E minus, okay, just as an example, but in general, it can be a fermion and an anti-fermion. So when we apply now the, so of course, which are spin 1/2, so different than 0. So when we apply now the charge conjugation operator to this fermion anti-fermion system, again, we have the -1 to the L coefficient that comes from the symmetry for the, okay, the exchange of the partial coordinates. Then we have for fermions, if you remember from the last lessons, 1 to the 1 that corresponds to the symmetry of the spin component of wave function that arise whenever fermions and antifermions are interchanged. So overall, so this applies to our state f bar, and so overall, the eigenvalue equation is -1 L plus S, because the +1 on the exponential cancel with this additional minus sign here, and then we have fermion anti-fermion state. Okay, so this is the general way charge conjugation operator applies to a system of particle-antiparticle in case the particle has a non-zero spin. So we showed the example of the vector mesons where the spin is 1, okay? And overall the effect is -1 L to the L plus S. And we also show the example of a generic fermion-antifermion pair. And here one has to consider the additional -1 coming from the Fermi statistics when you interchange fermion with antifermion. So overall the effect is the same, it's still -1 to the L plus S. All right. Let's go back to the slide. Okay, so this was about the charge conjugation. Let's now move to the third and last discrete transformation. That is the time reversal. So the time reversal invariance is defined as the invariance under the transformation that goes from t to -t. So it inverts the sense of the time, okay? While leaving all the position vector unchanged, okay? Now, the physical laws that are invariant under such transformation have no preferred time direction. So they can, with the same probability, with the same physics, occur in one direction or in the opposite direction of the time arrow, okay? And also, like parity and charge conjugation, the time reversal is a symmetry of strong and electromagnetic interaction, but it is violated by the weak interactions. Now, this is, however, different, because differently from the parity and the charge conjugation operator, the time reversal operator does not correspond to a physical observable. And in fact, there is no associated quantum numbers that is conserved as a consequence of the T invariance. So this is a main difference with respect to the previous ones. Okay. However, although the T invariance does not give rise to a conservation law, it leads to a relation between any reaction and the time reversed reaction or process in general. Okay. So let's consider, for instance, this reaction here. We have A plus B that goes into C plus D. Okay, and now the time runs in this direction, okay, from left to right. And also specified are the momenta and the spin of all the particles involved in this reaction. If we now apply the time reversal to this reaction, okay, we would obtain the T-inverted reaction, where now the initial state and final states are inverted, okay? So now the previously final state becomes initial state and vice versa. And due to the time reversal operation, we also inverted the sign of the momenta and spin, okay? So the situation is like this. This was our original reaction, A plus B that goes into C plus D, okay? And when you apply the T operator, this gives up, this turns out to be C plus D that goes into A plus B with inverted spin and momenta. Now, if weak interactions, if we neglect for the moment weak interactions, okay, then the symmetry under time reversal implies that these two reactions must be equal. The rate of this reaction, sorry, must be equal. So the probability for this reaction must be equal, okay? In fact, they are, that could be slightly different if one accounts also for the small T violation in the weak interactions. Now, a more useful relation between reaction rates can be obtained if we combine the T operator and the parity operator, so the T and the P invariants, okay? Let me remind you that under the parity operation, the momenta change sign, while the orbital momenta, and in general also the spin, of course, do not, okay? So under parity, we get from P to minus P, but then L remains the same because we have the product of two minus sign, okay? And so the same for spin. So the parity transformed of reaction 2, okay, where we exchange the one I showed before here, okay, with inverted initial and final state and inverted sign of parity and of momentum and spin is given by this one, okay, where of course the initial and final state are still inverted. The spin are the same because they are unaffected by the parity transformation, but now the momenta change sign again, okay? So it turns out that if both parity and time reversal are conserved in this process, then all three reactions must have the same rate. That means the same cross-section. And this is a very powerful tool, of course, to predict cross-section of, for instance, experimentally unmeasurable processes. Now, one can also simplify the reasoning. So if one averages over all the spin projections, okay, then you obtain the spin average reactions, okay? And you see here now the arrow as goes in the both direction. So under parity and time reversal symmetry, these two reactions, so if you look in one sense or in the opposite, they must be equal, okay, in terms of rate, so in terms of probability, or if you like, in terms of cross-sections. And this relation is called the principle of detailed balance, and it has been confirmed in many ways experimentally in a variety of strong and electromagnetic reactions when one do expect that both T and P are conserved. And also this principle of detailed balance, as we will study, is also exploited experimentally, okay, to make predictions also for processes that you cannot measure directly, okay? So in particular, as we will study, this was used to infer the spin of the pions, okay, in the 1950s. Now, this table here summarizes the action of the parity and the time reversal for a variety of variables, okay? So let's go through this table. For the position vector, the parity inverts the position, as you know, but the time reversal does not. For the momentum, both invert. This because it inverts the direction of space, and this because it inverts the direction of time. So one particle moving forward, then after time reversal will move backward, okay? What about spin? So this is the Pauli metric, so this indicates the spin. The spin is unaffected by the parity operator because it is an angular momentum, but it changes under the time reversal. The spin you can always imagine like classically like a spin rotating, okay? Suppose you have an object rotating clockwise, then if you apply the time reversal, this rotates counterclockwise, so it changes sign.
What about electric field? Okay, the parity, under parity operation, you get a minus sign because, for instance, you have, suppose you have a dipole, plus charge and a minus charge, then you apply the parity, you interchange their position, and so you change the sign of the electric field. Whereas this remains unaffected by the application of the time reversal. For the magnetic field, instead, it is a cross product of vectors, so it is unaffected by parity, but it changes sign under time reversal, and this can be understood in the following. So you know that a magnetic field can be generated by an electric current circulating in a coil. So if you revert now the sense of time, the current will flow in the opposite sign, and so we generate an opposite magnetic field. Then we have composite variables here, okay? So spin times magnetic field, and this is called the magnetic dipole moment. Spin times electric field, this is called the electric dipole moment. Or we have also this other combination here, okay, the transverse polarization, etc. Now, if you look at the magnetic dipole moment, this remains unchanged by both action of parity and time reversal. Whereas, if you, and also for this longitudinal polarization, no, sorry, this gets also opposite here. Now, if you look to the electric dipole moment, okay, you see that it is changed by the parity operator because the electric field changes sign, okay, but the spin does not. Whereas, and also by the time reversal, because in this case, the electric field stays the same, but now it's the spin that is inverted, okay? So, what is the point I want to make here now? If P or T is conserved in a certain process regulated by a certain interaction, then the Hamiltonian or the Lagrangian of that interaction cannot contain terms which change sign under the parity of the time reversal operation, okay? If in your Lagrangian or your Hamiltonian you have a term, even just one term, that changes sign when you apply P or T, then clearly the interaction that is described by this Hamiltonian is P violating or T violating, okay? Let's consider now particles with spin 1/2, okay? So expressing this term in terms of the Pauli matrices. So this particle can have a non-zero magnetic dipole moment, okay? Because you see sigma B stays the same under parity and also under time reversal, but cannot have an electric dipole moment, at least if the process is regulated by electromagnetic or strong interaction, because these would change sign both applying P and applying T. Okay, what is an electric dipole moment? And in general, an electric dipole moment is a permanent asymmetric distribution of positive and negative electric charges, okay, with respect to some quantization direction, which is given by the spin direction, okay? And this is because, in fact, this scalar product, sigma times E, is not invariant under P and under T, okay? Now, why is this important? It is important because if you experimentally find some sizable non-zero electric dipole moment, then in electromagnetic interaction or a strong interaction, then this would be a clear signal of something new, of new physics that is not explained by the standard model. And in fact, many high-precision experiments have been performed to search for a non-zero EDM in electromagnetic interactions, which, in fact, if observed, would reveal new physics beyond standard model. So it is a real new and very exciting frontier field in particle physics. Let me spend a few more words about the electric dipole moment. So suppose there exists a neutron with a non-zero electric dipole moment. We call it dE, okay? With the spin parallel to the electric dipole moment. So suppose this is your neutron. Suppose there is a non-zero electric dipole moment. That means that there is a permanent separation between the negative charge and the positive charge, okay? Really, overall, the neutron is neutral. So suppose that we start from this initial state where the spin is parallel to this dipole, electric dipole moment, okay? And the spin is anti-parallel to the magnetic dipole moment, dm, which is always true for the case of neutrons. So suppose this is our initial state with a non-zero electric dipole moment, so a non-zero permanent separation between plus and minus charge within the particle. What happens if we apply the parity operator? If we apply the parity operator, of course, the charges will be swapped, so the minus becomes plus, the plus becomes minus, okay?
So the charge distribution is inverted, and if you invert the charge distribution, you are also inverting the direction of the electric dipole moment. Okay. However, the spin, as we know, remains unaffected by the parity operations. Okay. And so in this case, electric dipole moment and spin are anti-parallel, whereas in the previous state they were parallel. What about now the magnetic dipole moment? The magnetic dipole moment remains unchanged because it must remain anti-parallel to the spin. So if the spin is unchanged, also the magnetic dipole moment is unchanged. Okay, but now the observation is that in case of a non-vanishing electric dipole moment, okay, it would be possible to distinguish between the original configuration and this final configuration, which is the parity mirror image of the first one. Okay, so you obtain this after applying the parity operator. And so since you can distinguish these two are not identical, that means that parity would be not conserved, or parity conservation would be violated. The other possibility is by applying the time reversal operation. So again, we start from this initial state, okay? Then we apply the time reversal operation. Now, the result is that the charge will remain unaffected, so the minus sign remain on the left and the plus sign remain on the right, okay? But due to the time reversal operation, now the spin will change sign. So the particle will spin in the opposite direction, okay? And as a consequence, since the magnetic dipole moment must always be opposite to the spin in the neutron, this also changes sign. However, the electric dipole moment will stay the same because the charge asymmetry is the same as the original one. Okay. So again, the electric dipole moment becomes anti-parallel to the spin. Okay, and so again, this final state, this final configuration is distinguishable from the original one. In the original one, EDM are parallel, now they are again anti-parallel, okay? So therefore, again, in case of non-vanishing electric dipole moment, the time reversal configuration can be distinguished by the original one, and so time reversal will be violated, okay? Now, in conclusion, if the neutron has a non-zero EDM, both T and P invariants will be violated by electromagnetic interactions. What is now the experimental status, okay? So as anticipated, T is violated by the weak interactions, okay? We know that T is conserved in electromagnetic and strong, but it is violated by weak interactions. Now, this results in an extremely small standard model prediction for the neutron EDM, okay? So the neutron EDM is predicted to be non-zero, but extremely small, 10 to the minus 32, this is the electron charge times centimeter. And this is so small because it can only be it can only be allowed by the T violation, which is possible only in weak interactions. Okay. Now this is the predicted value by the standard model, and this is now the present experimental precision. Okay. You see, we are still far away by many order of magnitudes. Okay. So in order to test this, we would need a precision at least up to 10 to the minus 32. Okay. However, there are, as you know, many extensions of the standard model, such as the supersymmetries, for instance. And in many models that goes beyond standard model, this EDM is much, much larger than expected by the standard model, okay? So for instance, for the supersymmetry, this EDM is predicted to be 10 to the minus 26. So it indeed more or less the same order of what we can now reach experimentally, okay? So the experimental search for a neutron EDM is therefore of utmost importance because it can provide evidence for your physics, okay? So test for models of physics beyond standard model, okay? Because we have now essentially the required precision at least to test some of these beyond standard models predictions, okay? What about the electron, okay? The standard model for the electron EDM is much smaller, okay? So it's order 10 to the minus 38 centimeter. And so, of course, now it's completely out of our present experimental precision. Now, this diagram tells you essentially how the precision in this experiment has improved in time. So starting from the 60s up to, let's say, 10 or 20 years ago, for the neutron in black and for the electron in red. So you see, decades after decades, the precision of the experiment has improved, okay? And so we are now going down in this scale, logarithmic scale here. So more or less the level we have here is around 10 to the minus 26, okay? And as I was showing before, the standard model prediction for the neutron in gray and the electron in red are much, much lower, okay, to the present experimental prediction. However, in this region here, we do have prediction of EDM from different models, supersymmetries, multi-Higgs, etc. So if you now project our precision, so this is the present experimental precision for the neutron and the electron EDM, okay? This is the projected precision for the future EDM experiment in the next years. So we will be able completely to cover to test all these models, okay? Where still the standard model prediction would require a higher precision. So this is indeed a frontier field in particle physics. Okay, you can search for new physics either at the most powerful accelerator, such as the Large Hadron Collider, trying to produce new particles, such as supersymmetric particles, or you can infer the existence of new physics beyond standard model by testing, for instance, existence of a non-zero electric dipole moment for the neutron or the electron. Okay. Just to tell you, there is also in Ferrara a group, okay, working also on this field of research. Now, the last thing I want to touch is the CPT theorem, okay? And it is a fundamental theorem of quantum field theories and tells the following, that all interactions are invariant under the successive operation of the charge conjugation, parity, and time reversal, taken in any order. So, however, whatever you combine these three operators, but you apply all of them, you would obtain exactly the original state, okay? And this is true for any kind of interactions, also for the weak interactions. So we can state this theorem in a more formal way as follows. So if a theory of interacting field is invariant under the proper Lorentz group, that includes the Lorentz transformation plus rotations, then it will be also invariant under the combination of successive application in any order of the charge conjugation, the space inversion, and the time reversal. And a fundamental consequence of the CPT theorem that has been verified experimentally to an extremely high precision, as I will show you in a moment, is that particles and antiparticles must have the same mass, the same lifetime, and equal and opposite electric charge and magnetic moments. So this is a pure prediction based on the conservation of CPT. And what is now the experimental status? Okay, here you see the many experiments have been performed in the past decades to test the CPT theorem to an incredibly high precision. So in the first result, you see the charge over mass ratio for the antiproton divided by the corresponding for the proton. And this ratio is essentially 1 up to an incredibly high precision. This is now about the mass of the electron and the positron. And again, the difference is consistent with 0, okay, up to a very high precision. This is about now the decay time of the mu plus and the mu minus, and the ratio is 1 up to an incredibly high precision. And it is about now the magnetic moments for electron and positron, and again the difference is essentially 0. Okay. Now, if C, so the charge conjugation, were not violated by weak interactions, all these equalities would result by the sole conservation of the charge conjugation. However, if C is violated, since we know that C is violated by the weak interaction, all these equalities derive by the more general conservation of simultaneous C, P, and T operations. Okay. Another important consequence of the CPT theorem is that since, as we will study, CP, so the combination of charge conjugation and parity, is violated by weak interaction, then also T is violated by weak interaction, because overall CPT must be conserved. And therefore, also the search of T violating processes has acquired a great importance. And the first direct observation of a time reversal violation in a weak interaction has been achieved by the Babar collaboration in California in 2012 by studying the time evolution of an entangled neutral B meson, so a system made by the B0 mesons and the anti-B0 mesons, where the B meson, as we will study, is a heavy meson made by a light quark and a bottom quark, which is quite heavy, okay, beauty, okay? So this was the first and probably also the only one at present, the result showing experimentally the effect of violation of time reversal, okay, which is of course only possible in weak interactions. Now, direct searches of T violation in strong interaction have been also performed, okay, by the application of the principle of detail balance that I was showing before to forward and backward reactions, okay. So if the strong interaction is invariant under T and P, then the matrix element for the forward and backward reaction must be equal, as we've shown before, okay. From the study of the reversible reactions of proton on aluminum that gives you alpha particle on magnesium nuclei, it was concluded that the amplitude of any T violation in strong interaction must be smaller than 5×10⁻⁴. So this is, let's say, an upper limit for the time violation in strong interactions. Of course, we expect that this is in strong interaction, time reversal is completely conserved. So this will be 0 exactly. And now let me conclude with this summarizing table. Okay, so what you see here is a table where the columns are the strong interaction, the electromagnetic interaction, the weak interaction, and N tells you whether the quantum number is additive or multiplicative, okay? So the quantities you see here are conserved by all three interactions. So of course, energy and momentum, of course, angular momentum, but also baryonic number. We have seen today that it is conserved by any interaction. Leptonic number, this we will study next in the course, okay? But also these quantum numbers are conserved by all three interactions, with the only exception of the neutrino oscillation phenomenon, okay, that we will study, of course, at the end of the course, which in fact allows a violation of the leptonic flavor number for neutrinos only, okay? Then electric charge, of course, is all conserved by all interactions, and CPT, so the simultaneous application of these three operators, discrete transformation, is also conserved by the three interactions. Now, what about parity and charge conjugation? As we have seen, they are both conserved by the strong and electromagnetic, but they are violated by the weak interactions. Then CP and T separately are also conserved by the strong and electromagnetic interaction, but they are slightly violated by the weak interaction. This we will study, of course, in the proper time in the course. So the CP is in fact violated in some meson decay, neutral meson decay, such as the K0, K0 bar. Okay, there should be an antiparticle here. Also here is not visible. So K0, K0, B0, B0. And now very recently, so this is a discovery of the last year from the LXB experiment, also on the D0, D0 bar, okay, system. So CP is slightly violated in weak interaction in some decays, and as a consequence of CPT theorem, also T must be also violated in weak interactions. And then we have other quantities that we will study next in the course. So the strong isospin, the third component of strong isospin, and the strangeness. So these are all conserved in strong interactions. Only the last two are conserved by electromagnetic interactions, and none of those will be conserved by the weak interactions. And then just to complete the table, okay, now we get here the antiparticle. Just to complete the table, this gives you the lifetime and interaction range of these three interactions. This we have already discussed before. So the lifetime of typical strong decays is extremely short, order of 10⁻23 seconds. For electromagnetic decays, it is, let's say, 3 orders of magnitudes longer, order of 10⁻19 or 20 seconds. And it is much, much longer for the weak decays, okay? So the weak decays are by far the slowest decays, with a lifetime of the order of 10⁻12, but there is also a big range of values here. What about the interaction range? This we discussed already with the Yukawa theory, if you remember. So for the strong interaction, it is very small, of the order of the proton size, so order of 1 Fermi or 10⁻13 centimeter. It is infinite, as you know already, from the electromagnetic interaction. If you put an electric charge into space, you generate an electric field in the full space, so up to infinite distance. And it is extremely small for the case of weak interaction, so even smaller than the dimension, than that is 1,000th of a Fermi, 100 of a Fermi, okay? This is the present spatial resolution we have as experiments, okay? Ok, questo completa la lezione. Allora abbiamo trattato quindi oggi le simmetrie discrete di parità, coniugazione di carica e time reversal. Abbiamo discusso in particolare questo, diciamo, caso molto interessante dell'electric dipole moment, perché è una porta eventuale di accesso per nuova fisica oltre il modello standard. E il vantaggio dell'electric dipole moment è che per eventualmente trovare nuova fisica hai bisogno di apparati sperimentali molto più semplici, molto più economici dei grossi, enormi esperimenti che invece abbiamo al CERN, all'Hadron Collider. Okay? Quindi è una ricerca altrettanto fondamentale, altrettanto di punta, ma che richiede costi e risorse umane e materiali estremamente inferiori. Okay? Quindi questo è il grosso vantaggio di questi esperimenti. Sono esperimenti di altissima precisione, ma che non richiedono elevate energie, quindi richiedono degli acceleratori tutto sommato molto piccoli e relativamente economici. Ok, la prossima volta, dunque mi sa che noi ci vediamo dopo Pasqua adesso, quindi la lezione del 15 salta perché è ancora l'ultimo giorno delle vacanze di Pasqua, e quindi noi ci rivedremo il 16 aprile e diciamo, completeremo questo argomento facendo una serie di problemi che vi ho già messi nelle slide che trovate online, quindi se avete voglia potete già cominciare a provare a risolverli voi in base a quanto abbiamo visto oggi, e poi sicuramente li faremo insieme poi la prossima lezione. Ok, avete domande, dubbi, qualsiasi cosa?
Tutto ok.
Io per ora no.
Ok.
A posto.
Va bene. Allora, se non ci sono dubbi o domande, ci salutiamo, vi auguro delle buone vacanze, state a casa ovviamente, ci vediamo poi il 16 aprile. Adesso interrompo la registrazione.
Grazie.
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 Grazie a voi.